Welcome to Topic 3, Gases and Their Properties. I'm Mr. Rast, and I'm going to take you on a little journey of learning about gases. All right. One of the physical properties of gases that's important that we'll be reviewing in this lesson is pressure. Pressure is the force applied by a fluid, which can be a gas or a liquid, on the surface. Notice I don't have solid in there. Last topic we talked about temperature, and as you know, temperature is the kinetic energy of all the particles in an object. So in a solid, though, the particles are not free to fly around, they're vibrating. But in a fluid, such as a gas or liquid, they're able to move around. And as they move around, they can collide into each other or collide into the surface of another object. How much force they collide into those surfaces is what the pressure is of these fluids or gases. Now, I want you guys to be familiar with some measurements that we'll be using with fluids, and those common measurements are atmospheres, torr, and kilopascals. There are other measurements for pressure, but these are the ones that we will be using most in my class. I would like you guys to familiarize yourselves just for this test. On the final exam, which is cumulative, I will give you these keys, but for this test, I'd like you to familiarize yourself with being able to convert from any one of these back and forth. Now, I've got all the conversions here. In other words, 1 atmosphere in 1 atmosphere it's a 1-to-1 ratio, obviously. The standard atmosphere pressure to torr, for every 1 atmosphere there's 760 torr, and for every 1 atmosphere there's 101.325 kilopascals. I have 1 torr, what that's equal to, and 1 kilopascal, what those are equal to. The most common conversion that I'm familiar with is this top line. If you remember the top line, that 1 atmosphere is 760 torr and 1 atmosphere is 101.325 kilopascals, you can convert into anything else using dimensional analysis. And now when I say dimensional analysis, if you're thinking I don't know what Mr. Rast is talking about, please review Topic 1, Lesson 2, when I go over how to convert things using dimensional analysis. Notice, if you remember this line here, you do not have a relationship directly from torr to kilopascals. And you know what? I forgot to put the unit here. So I'm going to do that right now. Hold on, and I'll be right back. Okay, I just put the unit in my PowerPoint for future lessons. It bothers me when I forget units. All the other ones have units. Yes, yes, yes. So anyway, as I was saying, there's no relationship directly, if you remember the first line, from a torr to kilopascal, but you do have atmospheres in common, so you can use a 2-step dimensional analysis. For instance, you could convert torr into atmospheres and then your atmospheres back into kilopascals using 2-step dimensional analysis. So for this test, remember that 1 atmosphere is 760 torr, and 1 atmosphere is also 101.325 kilopascals. For me, most of my questions will be in atmospheres, and that's why I suggest that this top line would be the one that you'd want to remember, because most often I'll give you questions in atmospheres. Okay, let's talk about some laws. We're going to talk about 3 different laws, gas laws, with this first topic, and the first law is Boyle's law. In Boyle's law, the volume of a given amount of gas held at a constant temperature varies inversely with pressure. What I'm saying is that if you're not, the temperature is constant, but if you change the volume, you will inversely change the pressure. So let me give you a little illustration here. If there is a cylinder, an airtight cylinder, and we're going to say it's 5 liters, and inside here it's got an internal pressure of 2 atmospheres. If we add some force here, if we push down on the cylinder and decrease the volume, we're going to say to 2.5 liters, the pressure inside increases to 4 liters. So by inversely related, what I'm saying here is that in the first situation, I have a volume of 5, and the second one I have a volume of 2.5. As the volume decreases, the pressure increases. That's inverse relationship. As one decreases, the other one increases. So as the volume decreases, the pressure increases. You might have, I'm sure you've experienced something like this, taking like a bicycle pump and pressing down on it, like maybe putting your fingers and making so it doesn't let any air out. And as you press down on it, it gets harder and harder to press down, and it'll kind of spring back up. That's what you're doing right here. That's Boyle's law. You're not changing anything about the temperature, you're just playing with the volume and pressure. And how that's represented is P1 V1. That means the first situation. So the first situation here, pressure times volume, so that would be 5 liters times 2 atmospheres, should be equal to the pressure times the volume in the second situation. So if you take a look at that, the first situation, you'd have 2 atmospheres times 5 liters, which would be 10 atmosphere liters. And in the second situation, you have 4 atmospheres times 2.5 liters, which is going to multiply together to be 10.5 or 10 atmosphere liters. So that's Boyle's law here. I'm going to give you an example of what you would see, how you would see Boyle's law in a problem and how you would solve something like that. So a question that might involve Boyle's law would look something like this. If a 2.5 milliliter cylinder had an internal pressure of 0.95 atmospheres, then it is compressed to 1.1 milliliters, what would be the new internal pressure? So to do this, let's first take a look at what information we have here. No, like there we go. We have the initial volume. Oh, that's not good. Okay, the initial volume. It's not writing very nice for me today. The initial volume is 2.5 milliliters, and the first pressure was 0.95 atmospheres. We have a new volume. Oops, a new volume. So that's our second one, is 1.1 milliliters. And our new pressure is what we're solving for. So our second pressure is what we're solving for. So I'm just going to put that as X. That's what we're solving for. And Boyle's law says that the pressure and times the volume in the first situation will be equal to the pressure times the volume in the second situation. Since we're solving for the second pressure, I'm going to set this to be equal. I'm going to cross multiply. I'm going to take the second volume and slide it as a denominator here. So if I rearrange this equation, P1 V1 over V2 would equal P2, which is X. That's what we're solving for. So let's plug these values in. So whenever we're solving this stuff, the first thing you do is write out what you know from the problem. And the second thing you do is use what equations you know and rearrange them to solve, for what you're looking for. And then the third thing you do is solve it. Plug in those numbers. So P1 is 0.95 atmospheres. And that's going to be multiplied by V1, this first volume, which is 2.5 milliliters. Okay, and that's going to be divided by, where's my mouse? There it is. The second volume would be 1.1 milliliters. Milliliters cancel out with each other, and we are going to be left in atmospheres. Always show your work. This is a great way of making sure my atmospheres is a numerator, and that's the only unit I have left over. So show your work with units. It's mandatory in my class, guys. So we do this, and we would say that 0.95 atmospheres times 2.5 milliliters is this, divided by the 1.1 milliliters, and we have this as our answer. And the question has two significant figures, right? Two significant figures here, two here, and two here. So our answer is going to be with two significant figures. So rounding this question off to 2 would be 2.1. The 5 would round the 1 up. So we would have 2.2 atmospheres. That would be our answer. So if we were to take a 2.5 milliliter cylinder, press it down to 1.1 milliliters, the pressure, which used to be 0.95, would increase to 2.2. And that is, my friends, an example of how you would see gas laws. You will notice that in these gas laws, you have 4 variables, and questions will always give you 3 of them. I'll give you 3 variables, and you just have to solve for the other one. You're going to have to rearrange the equation and solve for it. Okay, let's take a look at some of the other laws. Charles' law, the volume of a given mass of a gas is directly proportional to its Kelvin temperature at a constant pressure. So what this is saying is the pressure isn't changing. What's changing here is your temperature and your volume. So for instance, if you've got a container and this cylinder is free to move up and down, and it's pressing down on the gas, and the gas is holding it up because airtight, it can't go all the way down. It's got 1 atmosphere inside here, and it's holding up this cylinder. If we heat it up, as we learned from the last topic, temperature is kinetic energy of the particles. That means if it gets hotter, the particles are moving around faster. So if you heat it up, they start moving around faster and applying more force, more pressure to the cylinder, and so the cylinder rises because there's more activity inside the cylinder due to the increase in temperature. So the pressure will still be the same, but what happens is the volume expands because it's allowed to expand. So the volume expands and the pressure remains the same, but because you heat it up, it expands here. An example of this would be like taking a balloon. A balloon will always have the same amount of pressure inside the balloon as outside the balloon. So if you heat up a balloon, it will expand, and if you cool down a balloon, it will contract. To keep that, the volume will adjust because it'll always have the same pressure as the outside of the balloon. So this is a direct relationship. As volume increases, so does temperature, and then the second, it should be equal to the second situation here. So again, a problem like this would be giving you 3 of the values, and you would have to rearrange this equation to solve for the 4th value. The next law is Gay-Lussac's law, and the pressure of a given mass of a gas varies directly with the Kelvin temperature when the volume remains constant. Gay-Lussac's law, the volume is constant. So it would be a container that's rather strong and airtight, like a pressure cooker. So a pressure cooker is sealed so the volume is constant. The pressure increases in the cooker as the temperature increases. So as you heat something up in a pressure cooker, the pressure gets greater and greater and greater inside the pressure cooker, which allows the water to stay as a liquid and be hotter than its normal boiling point. Because if you don't have it under pressure, we know from the last topic that the water will boil at 100 degrees Celsius, and more energy will just cause it to phase change into steam. But if you have a pressure cooker, you can change the activity on the phase diagram and make it hotter. So pressure cookers have water inside of them that are hotter than their normal boiling point. Anyways, it is directly related. So as you increase the temperature, you will increase the pressure. It's directly related. So the pressure and the temperature in the first situation will be equal to the pressure times the temperature in the second situation. So in other words, if you don't have the cooker on, maybe it's 1 atmosphere in here and it's 20 degrees Celsius. As you increase the temperature and it goes up to 100 degrees Celsius, the pressure in here will directly increase. Thing to note for both Gay-Lussac's law and Charles' law is we are talking about Kelvin temperature. Very, very, very important here. So let me see here. We are talking about Kelvin. Very important. Highlight that in your notes, guys. We are not using Celsius. We are not using Fahrenheit. We are using Kelvin. If you don't convert it into Kelvin, you will make mistakes. For instance, you can have 0 degrees Celsius. Kelvin's an absolute temperature, though. If you have 0 degrees Kelvin, there's no activity, there's no energy, which means these guys aren't moving around at all. But if you have 0 Celsius and you have a 0 as a denominator, that would give you an error. And if you had, like, you can have negative 1 degree Celsius. My freezer is cooler than that, and yours is too. Then you would have a negative value. So if you're solving for volume and you have a negative temperature, you would have a negative volume, which is not possible to have a negative volume. So make sure that you convert into Kelvin. And as a reminder, to get into Kelvin, if you forgot, it is your Celsius temperature plus 273. Well, I wrote that with the mouse. That looks pretty ugly. I'm just curious. Let's see how it looks with my pen. Kelvin equals Celsius plus 273. There's a reason I have this tablet. That looks a little prettier. All right. So your workshop here is there's 5 little practice problems. Again, you'll see that I'm giving you 3 values. Here I've got volume, I got a volume and a pressure in the first situation, and then I've got a new volume and I'm asking you what the pressure is. So you're going to have to use one of those 3 laws to solve these problems. There will be one of those 3 laws. Now sometimes these ones don't, these are mathematical, but often chemistry questions will ask you about these laws with no numbers. They might just say, if you have a bicycle pump, like I gave you the example before, if you have a bicycle pump and you press down on it and as you decrease the volume it gets more pressure, that would be an example of which law. That would be a realistic question that you could see on a test. So you got to be familiar with these different laws. I would say, to help you remember, they all have one thing constant. In Boyle's law, what's constant is temperature. Notice there's no temperature here. So for me, I remember Boyle's law because I think of Boyle, I think of boiling water, I think of very hot water, and I think of hot in temperature. So whenever I think of Boyle's law, I think it's the temperature that's constant. When something's boiling, the temperature is constant, and that helps me, and maybe it'll help you to remember when to use Boyle's law, because it's sometimes you have to know the name of it, not just the formula. So Boyle's law is when temperature is constant. So if you're just dealing with pressure and volume, that's Boyle's law. With Charles' law, what's constant here is pressure. The pressure is constant in both situations, but the volume changes directly with the temperature. And I remember Charles' law because I had a friend in high school that was really stressed all the time. He was always concerned about his grades. He was always concerned about just everything in general. He couldn't relax. And I always think of Charles as being under pressure. If there's one thing constant about Charles, he's under pressure. So if you can think about one of those people that are under pressure, maybe, or think about my friend Charles, that might help you to remember that Charles is always under pressure. So with Charles, we're only talking about volume and temperature as being variables. The pressure will always be constant. I do not have a trick that I had thought of for Gay-Lussac's law. But to be honest, what I do with Gay-Lussac's law is I think, okay, I know Boyle is temperature, I know Charles is pressure, so Gay-Lussac's is the last one, that's volume. Uh, I just I just remember Gay-Lussac's law because of process of elimination personally. Okay, so give these a try. Um, we'll go over those in class, and maybe I'll put a forum up and you can share answers with this as well. But give these a try, and if you need help, make sure you ask me. That's what I'm here for. Don't forget that you have to answer in Kelvin, not Celsius. So you'll have to convert this out of Celsius into Kelvin. But if I have the question in Celsius and I want to know what the new temperature is, um, you need to tell me in Celsius. So you have to convert this 89 into Kelvin and then solve it, and you're going to have your answer in Kelvin. Then you're going to have to subtract 273 from that answer so that you answer back in Celsius. In other words, if the question's saying something in Celsius, you answer back in Celsius. If it says something in Fahrenheit, you'd answer back in Fahrenheit. So don't answer in Kelvin, even though that is the scientist's temperature. We usually take the measurements in Celsius. So, and you'll see in number 4, if you don't convert, this is 0 degrees Celsius, you're going to have some big errors. So make sure you convert that, and good luck. And I will talk to you guys soon. Bye.